So we are group number 4, and we're gonna present on the fourth pillar of statistical wisdom, that is intercomparison. My group members are Keziah and Sai, and myself Tushar. So this term intercomparison was first coined by Francis Galton way back in 1875. He introduced this concept of intercomparison in his article Statistics by Intercomparison. He proposed that the comparison could be made without external standards by using percentiles like the median and quartiles. And for example, if we take an example, it's like a ranking talents in a population group based on biographical data without numerical measures. So the official, I mean, the standard definition which is being given by Francis Galton is that it is an statistical concept where comparisons are made strictly based on the variation within the data itself without relying on any external standards. So this idea allows for the comparison to be made directly from the data, making the whole method very flexible and robust. There are few other developments in this domain of intercomparison, and it was given by Francis Edgeworth. He simply covered the extension idea of the intercomparison, which will be covered by my group mates in the upcoming slides, followed by William Gossett in 1908, known for his work at Guinness Brewery and his article on probable error of a mean, and then followed by Ronald A. Fisher. Further, he redefined the statistical method, including those related to the intercomparison. Next slide. There are certain few key concepts which is being covered, and those are percentiles, what I have mentioned earlier. It's a simple method of ordering data and using percentiles like mean and quartiles to make the comparison, where we need not have to go for an complex calculation. Just ordering and counting is enough. Then Gossett contribution. So this Gossett worked at Guinness Brewery, and he recognized that the need of statistical method for quality control. So later on, he developed the concept of t-distribution, published under the pseudonym of student due to company's policy. And he also coined the term of t-distribution. Again, it will be covered in the upcoming slides to understand the distribution of a sample mean, specifically when the data set is very small. And then normal distribution and standard distribution. So when dealing with the large sample size, a statistician often use the standard deviation to describe the distribution. For small sample size, adjustments are necessary for to accurately estimate the distribution. So if we go on, simplified explanation for intercomparison, imagine you have a test score of a class. So instead of comparing these scores to an external standards like national average, you compare them with the class itself. So you could use the median score or divide the score into quartiles to see how students compare to each other. And next slide. Yeah. So this is the probable error of a mean by students. It is given by William Gossett. So he explains that in any experiment uh, uh, that can be seen as a set of trial or experiment that could be performed under the same condition. So these experiments are a simple sample taken from a large population. So the value of experiment lies in their ability to help us understand the statistical property of the population from which the sample is drawn. So it's often said that the main focus is demanding the mean or the average of of this population. And again, we can imagine like conducting an experiment multiple times under the same condition. So this repeated experiment form a sample that represents a large group population. The goal is to figure out the average outcome of the population based on your sample. So if you have many experiments, you can estimate that this average accurately. But let's suppose we have a fewer experiment. Then we come across two problems. The first one is the average result of your sample might not match the true population average. And the second issue is you might not have the enough data to understand the population characteristics accurately. So, in order to deal with these issues, statisticians often assume that the data follows a normal distribution, the common, well understood shape like a bell curve. This assumption simplifies that the calculation, especially when using the standard deviation, like when we measure how to spread out our data to estimate the average and its accuracy. Next. So this graphical representation, what you see is student t distribution. So Gossett developed this in order to know the student t distribution, which is used when estimating the mean of a normal distribution population in a situation where the sample size is small. So this t distribution has n minus 1 degree of freedom, where n is the sample size. Gossett assumed that the sample mean and the sample standard deviation were independent. So we can say that this is true for a normal distribution, but not for other distribution. This figure 4.2 represents that the t distribution of for z with 9 degree of freedoms. So this dashed line represents a normal distribution with the same standard deviation. And Gossett even noted that the t distribution, the solid line, closely follows the normal distribution, the dashed lines, but deviates more for a large value. I mean, for the extreme data points. So Gossett provided this table for calculation significance probability for the different sample size, mainly from n is equal to 4 to n is equal to 10. So yeah, so again, if you see this diagram, the solid curve represent the t distribution for z with 9 degree of freedom, whereas the dash curve represent the normal distribution with the same standard deviation. X-axis is the distance of the sample mean from the population mean, whereas y-axis is the probability density. So the solid curve shows that how t distribution account for more variability in the trial compared to the normal distribution, making it more reliable for the small sample size. And so Gossett used this data to show how you can make conclusion based on the data itself. So without needing to compare to some external standards. This method allow you to calculate the probability like p-value directly from the data. So that's my part. Over to Sam.
So thank you, Tushar. So my name is Sai Siddish, and I'll be continuing with the presentation. So far, Tushar had been explaining the story or the invention of the t-test. Now we'll look at how the t-test got, advanced and popularized, and what role did Carl Pearson and Ronald Fisher play in that. And also we'll look at the remarkable contribution of Edgeworth, Francis Edgeworth in the 1880s, who took the probability scale to the social science field. So yeah, so in spite of publishing, the Gauth's article in Biometrica, it did not get the much expected attention. So Carl Pearson went on to publish this in tables for statisticians and biometricians in the year 1914, but still they weren't getting the expected attention. So one person who saw the magic in the t-test was Ronald Fisher when he was about to graduate from Cambridge in 1912. So Fisher knew that there was no proof to the t-test, and he knew that viewing that from the in terms of multidimensional geometry could yield a fully rigorous proof. Regarding this, he wrote a letter to uh, you know uh, Gauss saying that this proof can be explaining the proof, but unfortunately, William Gauss was not able to interpret it, and he even forwarded it to Carl Pearson, and he was also not able to interpret it. So Fisher did not get any response from Gauss, but he went on to publish it in Biometrica in the year 1915. So but still it was not very it was not getting that much of an attraction in the statistical forum. So finally, in the year 1920s, when Fisher was working on agricultural problems at Rothamsted Experimental Station, he had seen the mathematical magic that freed the t distribution from and its dependence on the standard deviation. So based on this, Fisher went on to invent the two sample t-test, which gained a lot of attention. Along with this, he also derived the distribution theory for regression coefficients and the entire set of procedures for analysis of variance. To give an current example of independent two sample t-test, let's take in the current scenario, BCCI is not really happy, or like they want to check the performance of head coach Gautam Gambhir currently and compare it with Dravid's era. So they can take a test of Indian team's performance in the ODI, especially versus Sri Lanka in ODI, and compare the performance of Indian team under the mentorship of Dravid, and compare it with the mentorship of Gautam Gambhir, and they can find it out whether is there any statistically significant differences in that, or is it by chance. And finally, in Fisher's book named Statistical Methods for Research Workers, he goes on to explain the important contribution of Gauss in the Statistical Forum, which was published in the year 1925. So now let's look at the remarkable contribution of Francis Edgeworth in the year 1880s, who took the problem to the field of social science. So in a meeting of British Association for Advancement of Science in Aberdeen, Edgeworth presented his method in the context of two examples. One was purposefully fanciful, and another one was related to social science. For the first one, he tabulated the number of dactyls, which is a metrical foot of a long syllable followed by two short syllables, in Virgil's one of the famous poetic works named Aeneid. So here is the table. So he took the table, he took a segment of Virgil's poetic work Aeneid, and he tabulated for each row and column sums, mean, and what in his terminology was called as fluctuations. In today's terminology, it could be translated to twice the amount of empirical variance. So he found it for each and every row and column sums, means, and fluctuations. This was the first example given for him for his work. Then he moved on to the social science example, where he took the death rates for 8 years in 6 English counties, and he did the same for each row and column. He went on to calculate the sum, mean, and fluctuations. So diagram 4.5 explains that. So it's an illustration of the example, and he goes on to find the same thing. One subtext or a remarkable thing that we could see from Francis Edgeworth's work was that the analysis was completely based on internal variation in data, which in modern terms or Galton's terminology called as intercomparison. So to finally sum it up, we can call Edgeworth's work as a series of missed opportunities, numerical errors, and algebraic clumsiness. But nonetheless, he contributed a lot to the field of statistics, and the future statisticians were able to build upon this and do well. So that is it from me, and over to Keziah, who will be continuing with the further parts of the presentation. Thank you.
Thank you, Sai. I am Keziah, and I will be continuing with the last part of our presentation. So, towards the mid last half of the 20th century, with the emergence of computers, computational methods for assessing data variation emerged. So, the first one was the jackknife method, which, estimates variability by removing one observation at a time. So, say you have a class of students and you want to check their average height. So, in this case, you will remove one student at a time and measure the average height each time. The second one is cross validation, which involves dividing data into subsets and performing analysis on each subset and comparing results. So, say they're trying to construct a model to check the prices of houses. So we'll gather data on the prices of houses, say in a particular locality. We'll divide it into 5 subsets. So we'll test our model on 4 subsets, and then we will compare the results with the last subset. And the last one is the bootstrap method, which involves repeatedly sampling data with replacement and calculating statistics to estimate variability. So moving forward, these are the propounders I previously mentioned about. And moving to the last part, which is the pitfalls of intercomparison. So, a theory that was proposed by William Evans about a connection between sunspot activity and business cycles. It was proposed in the late 1870s. And to give a briefing, sunspots are dark patches on the sun that appear and disappear in cycles. So Evans suggested that these cycles might be linked to the business cycles. He thought that there was a similar pattern for about 10.5 years, and he found some evidence in grain prices in India as well. However, the exact timing of these cycles and the economic cycles didn't always match, and thus it created challenges for his theory. So, regarding the criticisms, critics pointed out that sunspot activity seemed linked to other unrelated things, like the outcome of boat races or death rates. So, they suggested that people might find patterns in data even when there is no real connection. So, random data can sometimes show patterns over a short period. So, this can lead people to think there is a connection even when there isn't one. So, finally, it's like finding shapes in clouds. You might see a horse, you might see a dragon, but it's just a cloud. Similarly, finding patterns in data doesn't always mean you've discovered something real or important. So, that's it from my side. Thank you, everyone.